Let's do some simple analysis of our ping capture and see how ping works, or ICMP, and also ARP, and we'll try and draw the exchange of messages and the packets that are being sent. And we'll use wireshark to extract that information. So we have our captured packets here, 42 packets. Some are ARP, some are ICMP. Let's start with the very first packet. Let's see who sent it. And we look at the Ethernet source address and we check the hardware address and correspond or check that to our nodes. And if we confirm that node 1 has the hardware address that matches the source of packet 1 or frame 1, so node 1 sent that. Who does it send to? Well, the destination is a special case address here. This all F's address as a hardware address represents broadcast. So essentially node 1 sent this Ethernet frame to everyone on the same LAN. Our network topology was that on the same LAN as node 1, there was only one other node, node 2. But in general, there could be other nodes on the same subnet. So we'll try and draw this exchange, and what I'll draw is that a sort of a message, a time sequence diagram. We'll draw these vertical lines to represent the nodes and what's happening at those nodes over time. That one wasn't so straight. A bit better. And we'll see that for the first message, the source was node 1 and the destination was broadcast. So broadcast means that this message will go from node 1 to everyone on the LAN. We will not draw it sending to itself. It will go to node 2. So we'll draw a line saying this first message, which was an ARP request, was sent from node 1 to node 2. Now in our case there's only one other node, but in general, let's say that there are some other nodes. How do we draw that? Well, one thing I might do is show a few other lines to illustrate some other nodes in this network, and then show that this ARP request, to illustrate it's not just sent to node 2 but to other nodes. Maybe one approach is this, to illustrate that if there were other nodes on the same subnet as one, they would also receive this ARP request. It's broadcast. Then what happens next? Node 2 receives it. The request is saying, the summary information gives us good information about what the idea of this packet is. It's saying from node 1, who has the IP address 192.168.1.1? If you do, tell me at 192.168.1.11. And the details of that packet, we have a hardware type and a protocol type. The hardware type indicates the technology used at the lower layer, Ethernet, and the protocol type at the network layer, IP version 4. The size is the size of the addresses for each of those layers. In bytes, a hardware address or a MAC address is 6 bytes or 48 bits. An IPv4 address is 4 bytes or 32 bits. And this is a request. And then the actual addresses, so the sender MAC address, the sender IP address, and the target MAC address, which it gives us a special case of all zeros because we don't know it yet. If we knew it, we wouldn't have to ask what it is. Our target IP address is 192.168.1.1. We want to know the MAC address for node 2. So we send this ARP request. Node 2 receives it and sends back a reply because node 2 does know the MAC address. It sends back 192.168.1.1 is at this MAC address. And we could check the source and destination addresses to see that it is sent from node 2 to node 1. looking at the contents of this, the sender MAC address is that of node 2. The sender IP is that of node 2. The target MAC, we're sending it back to the source, node 1, which is 1.11 as an IP address. The result of this, when node 1 receives this second frame, it has learnt the MAC address, this 08002F. It has learnt the MAC address of node 1 and now can send the next ICMP request to node 1. Let's draw that. What comes back? An ARP reply comes back. And this was not broadcast, it's unicast from node 2 direct to node 1. And as a result, node 1 learns the MAC address of node 2 and now can send the IP packet for the ICMP request to node 2. You'll see ARP come up in many other exchanges. It's needed before we can communicate with a node with an IP address. Back to our capture, frame number 3. Now that node 1 knows the router hardware address, it sends the ICMP echo request. Destination is node 3, but because it needs to go to the router, it would actually physically go to the node 2. So the Ethernet frame and this ICMP echo request, destination of the next immediate destination is node 2. The IP header includes a variety of fields. Importantly, the source is node 1, the destination is node 3. The router will use the destination to know to forward it on. And the ICMP message, which is the purpose of this message, includes the information of the type of the message. It's a ping request, some sequence numbers, we'll see those change in a moment, some timestamp and some data. Let's draw it first. This is coming from node 1 to node 3, but it actually goes via node 2. I'll just draw a small arrow there to indicate that this packet's going to node 3, but node 2 forwards it on. And it is an ICMP echo request. I'll just write request. A ping request. It'll go to node 2, which will forward it on to node 3, and node 3 should eventually reply. Let's extend our diagram here. We need a bit more space. And let's go to reply, and then we'll analyze them in a bit more depth. Node 2, a little bit later, sends back an echo reply. So we'll draw that. The ICMP reply. And let's look at them in a bit more depth. First, we'll open the ping request. So we see the structure of the ping request. It's a frame of 98 bytes containing the Ethernet header, an IPv4 header, and then the ICMP packet. Let's first draw that as a general outline. We can draw the packet one way is simply to draw the headers. So we think we'll make some space. The structure is we have an Ethernet header, IPv4 header, simply IP, and then the ICMP packet. And the total length is 98 bytes. So let's record that on our diagram. What we'll do is draw this packet, and we can use such a picture as a summary of what's going on. We can understand the packet structure. And while we're here, let's check the length of each of the headers. What are the three components that make up those 98 bytes? If we go back to the packet in wireshark, and maybe we'll just close out and return to it. An easy way to see that, we've selected the packet number 3 or frame number 3. The Ethernet header, it may be quite small, but when we click on that, right down the bottom of the window, of the wireshark window, just above the start menu in Windows, is the length of the Ethernet header. It says Ethernet, 14 bytes. So we know Ethernet header is 14 bytes, IPv4 is 20 bytes, and the rest is the ICMP message, which is 64 bytes. So let's record those values. Ethernet header, we'll just note, is 14, IP was 20 bytes, and ICMP was 64. That's the total. 64 plus 20, 84 plus 14 is our 98 bytes. So we know the size of each of the components. Sometimes it's useful to stop there in terms of drawing the packet, but sometimes it's some additional information can be valuable to draw. Now, of course, each header is made up of a number of fields. It's difficult to draw all possible fields, but some fields are of importance, like the Ethernet header. Let's have a look at it. I'll double click to bring it up again in a different window. The Ethernet header, there are three fields: the destination, the source, and the type. Destination is that of, in this case, is that of the node 2, the MAC address of node 2, and the source is that of node 1. And the type indicates what's inside this Ethernet frame, which is an IPv4 datagram. So we could list those in the diagram if we want such level of detail. Maybe one easy way to list it is we have the source, the destination, and the type. And we could list the values there. Maybe the source equals, and I will not write the full value. The source is this value 08 through to 2F. Whereas the destination, you could write the full value, but as you see, struggle writing sometimes on the computer, save a bit of time. The destination, I've made a mistake here. The source is 5E. Destination is 2F. And let's, the source 5E, the destination almost the same, but it finishes with 2F. And this is really node 1 and node 2, but the MAC addresses. And the type says it's IPv4. So if you want to draw some of the field information, then you could do it as well. But as you can imagine, as we start to do the same for IP headers, we use up a lot of space. It's very hard to visualize all the different fields. So we may select some of interest. Maybe with IP, we've got a number of fields. What's of interest? Usually the source and destination IP addresses. Not the MAC addresses, but the source IP addresses. So in the IP header, has a number of fields: the version, IP version 4, the header length, the protocol, which indicates what's inside this IP datagram, which is an ICMP packet, and the source and destination addresses. Source is 1.11, destination is 192.168.2.21. And then the ICMP header, what's important inside there? Let's have a look. You may not draw it all. Look at the structure. It says the type of the message, it's a ping request. The code, if there's a subtype. A checksum's used for error detection. We have some ID and some sequence number, so as we do different pings we may have different IDs, and the sequence number, the first ping will be 1, the second ping in this set will be 2, 3, 4 and so on. There's a timestamp included to indicate so that when we get the response we can calculate the round trip time, and then the data. In this case I don't think there's any need to draw any of that information, but we should maybe at least keep track. It's an ICMP, I'll write it in here, echo request. So this diagram summarizes that one packet, and it's useful to at least draw the rectangles and the names of the header fields and the packets so you can quickly see what's the structure of the packet and even the size, and in some cases include some of the important fields on that diagram. You could try and draw it for the ICMP echo reply, be very similar structure but different values in the fields, and similarly you could draw the packets for the ARP request and ARP reply. So these two types of diagrams are very useful when you're studying protocols, the sequence of messages being sent between which node and which other node, and the structure of the packets being sent, the format of those packets. Try and extract that information from wireshark. What else do we see in this packet? Maybe the data is of interest. The data in ICMP ping requests are not important. Ping is just sending a message of any data. The data is not what's being communicated. It's just used to measure the time, the round trip time. So often the data is not important. What does ping do to create some fake data? Well, the first 8 bits actually are used for a timestamp, but if we see here from this byte onwards, we see it just increments the values. 10, 11, 12 as a byte, 13, 14, it goes up to 37 in this case. If the data was large, it would keep going. So it's just a way to create some dummy data, just to increment every byte. If we go back to our capture, see what other information we have. The echo reply, we've already drawn that on a sequence diagram. We could draw the structure, but it would look similar to the ping request. And then 1 second later, there's a second echo request. And then another second later, the third echo request, and so on. So this is the packets being generated about every 1 second by the source and getting a reply quite quickly. And the difference between the time of the reply and the request, for example, in this packet, 1.003 seconds. In this case, it's 3.3 milliseconds to 1, so the difference is about 2.3 milliseconds. Now, this is a difference recorded by TCP dump. There may be also some additional time from when the ping software gets it. So it depends upon the processing of your computer. So the actual difference reported in the output, if we see it, may be slightly larger than what's seen in TCP dump, but you should see a similar trend there. So we have a quick coverage of how ARP works and also ICMP, and how we can use Wireshark to draw the sequence of messages and also the structure of those messages.